Hello everyone, I'm Damien de from Paris Institute of Neuroscience, NeuroPsy. Today I'm going to talk about the biophysical model at the single neuron level. If you want more information about this model, you can have a look on our preprint that you can access scanning these QR codes. So this project starts with a question of seizure, electrophysiological seizures that are associated with epilepsy. These seizures are commonly recorded in humans thanks to electroencephalography and are associated with a high level of extracellular potassium if we look at the single neuron level. So we can see that during the seizure, we hear an increase of the extracellular potassium concentration. This is from experiments, and we wanted to reproduce this aspect with a model to understand better the underlying dynamics. So we proposed a model based on 4 variables. It's a reduced model based on Hodgkin's-like formalism with 4 different currents, a gating variable. This is a reduced Hodgkin's part, and 2 equations to model the change of concentration over time. So the model is constituted of 3 compartments: an intracellular compartment, an extracellular space, and what is called here external bus. It's a long range or large range. So each current are described with a conductance and the Nernst potential, and the evolution of the Nernst potential is due to the change in concentration of sodium and potassium over both sides of the membrane. This model can be seen as a slow-fast system. Indeed, the 2 first equations describing the membrane excitability have a very fast time scale and describes the spiking activity in the membrane, while the 2 other equations are very much slower and describes the evolution of the concentration. And here are examples of different patterns that can be reproduced by this model. And here are the first line for each pattern is a membrane potential variable, V. And here the 2 slow variable, and here it's the calculated extracellular potassium concentration. So we can see that when we observe bursting activity or seizure-like activity, there is a slow oscillation of the potassium concentration. From this system, we can study separately the slow and the fast part of the system. So here, if we look more in detail at the fast system, we can look at the phase plane where we have these 2 equations. We look at the derivative at each point, which gives us the flow, and we look for when each equation equal to 0, and then we obtain the null line here. The dark blue is the V null line, and the light blue is the N null line. And where the null line cross, we have fixed point. And so here we have 3 fixed points. And we can consider the slow variable as parameters and recalculate for each point of the evolution of the slow fast system how look like the phase plane of the fast subsystem. And so if we do that for the bursting activity we saw before, we can see that the associated evolution of the potassium concentration and sodium concentration will transform the phase plane and will allow the appearance of this bursting activity. This is the same for seizure-like activity, but we see that the way it is changed is different than the bursting activity. So this model have a reduced number of dimensions, so it facilitates the understanding of the dynamics, because we can use simple tools from dynamical systems, such as phase plane analysis, stability of fixed point, unit cycle, and so on. It's a way of making the link between biophysics and dynamics, because we use here biophysical description based on Hodgkin formalism. And this model allows to reproduce a large repertoire of patterns, and they correspond to also to the type of pattern that have been previously identified in the cases of epilepsies. So thanks a lot. If you have any question, you can send me an email at this address, and if you want more information, you can just read our paper. Thanks a lot.